Hello friends, now we will see one university question on design of a steel joist. This university question is for Anna University in the year May 2016. Here the simply supported joist is having a span of 4 meter effective span. It carries a total UDL of 40 kilonewton in service condition inclusive of self weight. We have to design an approximate section. Generally, for floor beam joist, channel beams are used. The spacing of the joist will be lesser in the range of 1.5 meter to 2 meter as against the I-beam girders, which are spaced at 4 meter, 5 meter, etc. Since the spacing is closer, generally beams with one flanges are provided and hence the channel sections are provided for the steel joist. Now, for the service condition, the load is given as 40 kilonewton. The load factor is 1.5. Therefore, the total uniformly distributed load is 60 kilonewton. The design bending moment is equal to WL by 8. Please note, it is not WL square by 8. This is total load. Total uniformly distributed load, factored load. So WL by 8, this comes to 30 kilonewton meter. FE410 means Fy is equal to 250 Newton per millimeter square. IS code is mentioning so many values for Fy. I was in the engineering department for nearly 40 years. I kept on using only Fy 250 only. I don't remember any other steel to be available in the market or having been used in the project. Fy is equal to 250 Newton per millimeter square. This is the ultimate stress, FE410. So unless otherwise specified, you take Fy is equal to 250 Newton per millimeter square. We have to choose an approximate section and then check it for bending moment, shear force, and deflection. Approximate value of ZP, modulus of plastic modulus of section is equal to M divided by Fy. M is equal to 30 kilonewton meter. Multiply this by 10 power 6. This is in Newton millimeter divided by Fy. Fy is 250 divided by 1.1. That material factor. Now that material factor goes to numerator. Let us add another 20% extra. So multiply this by 1.2. So 158.4 centimeter cubed. The whole thing we are getting in Newton meter, millimeter cubed. To convert this millimeter cube to centimeter cube, divide this by 10 power 3 so that you get this in centimeter cube. Because the steel tables are giving the properties of modulus of section and other properties in centimeters. So you divide this by 10 power 3. ZP approximate requirement is 158.4 centimeter cube. We are choosing ISMC 200. Always go for medium sections. If you are going for channel beam, go for ISMC 75, ISMC 100, 125, 150, 200, 300, 350, 400, like that. If you are going for I-beam, go for ISMB 200, ISMB 250, ISMB 300, 350, 400, 500, 600, etc. Go for medium section, ISMC. Now, the properties are ZP is equal to 181.9 centimeter cubed. R1 is the curved portion of the flange. Curved portion of the flange is 11 millimeter. Breadth of the flange is 75. Thickness of the flange 11.4 mm. B by TF ratio is equal to 75 divided by 11.4, 6.6. This should be less than 10.5. This is the limiting value for the rolled section. This indicates there is no buckling of the flange. Flange is not buckling. This is automatically taken care in the rolled sections. There is no need to carry out this check as all. As a matter of formality, this check is being performed. In case you are going for plate girder section, accordingly you have to check against the applicable limiting value for B by TF. there is no flange buckling. Now depth of the web, other than the curved portion, the total depth of the web is 200 mm for ISMC. R1 is 11 mm, curved portion at top. R1, curved portion at bottom, that is 11 mm. Deduct these 11 mm at top and bottom from 200, then you are getting 178 mm. This is the depth of the web for calculation of D by TW ratio. TW, thickness of web, 6.1 mm. D by TW, 178 divided by 6.1, 29 minus less than 67. Web does not buckle. This is also automatically taken care in the case of rolled sections, but this is very, very important to check against shear buckling. As in the case of plate girders, this ratio will determine what expression should be used for bending capacity. Whether ZP or ZT, it all depends on the factor whether shear causes buckling of web or not. Here there is no buckling of web. Therefore, ZP can be used without any further checks or validation. Now check for bending capacity. ZP into Fy by gamma m. ZP 181.9 centimeter cubed. Multiply this 10 power 3 so that this is in millimeter cubed. 250 Newton per millimeter square. Material factor 1.1. All these things are coming to Newton millimeter for the moment capacity. To get a decent value in kilonewton meter, let us divide this by 1 by 10 power 6. For converting this Newton millimeter to kilonewton meter, divide this by 1 by 10 power 6 so that you get it is 41.3 kilonewton meter. This is 41.3 kilonewton meter, not kilonewton. This is a mistake. 41.3 kilonewton meter. This is greater than 30 kilonewton meter. So bending capacity check is okay. Now let us go for shear capacity check. This is 30 kilometer. Now the shear value is total uniformly distributed load by 2, that is equal to 30 kilonewton. Shear capacity is equal to F by 3 into the shear area. Shear area is total depth of the beam into thickness of the web. 250 Newton per millimeter square, Fy, divided by root 3 into total depth of the beam, 200 mm. TW, thickness of the web, 6.1 mm. The whole thing gives you the shear force in Newton. To get this in as a decent value in kilonewton, divide this by 10 power 3 so that you will get this in kilonewton. It is 176 kilonewton. This is greater than 30 kilonewton. Therefore, the shear capacity check is okay. Now we have to check for the deflection. The allowable deflection is equal to L by 300. Here the span is 4000 mm divided by 300 mm, that is equal to 13.33 mm. IXX is equal to 1819 centimeter power 4. IXX is equal to 1819 centimeter power 4. Now we will use this formula 5 by 384 WL cubed by EI. 5 by 384 deflection coefficient for uniformly distributed load. W is the total load in service condition. Total load in service condition. That means 40 kilonewton. And not factored load. For deflection check, you have to consider only the service load, not factored load. 40 kilonewton, get it in Newton, multiply this by 10 power 3. Total load in Newton, 5 by 384 into L cubed. It is not L power 4. If it is uniformly distributed load per unit length, it is L power 4. Here, this is the total uniformly distributed load. When it is total uniformly distributed load, it is 5 by 384 into W into L cubed. L is equal to 4000 mm, 4000 cubed into EI. E is equal to 2 into 10 power 5 Newton per millimeter square. Then I is 1819 centimeter power 4. We have to convert this to meter power 4 so that all units are consistent. Now 1819 centimeter 4 should be multiplied by 10 power 4. Therefore, this will be in millimeters. Now this is the formula with all the applicable factors. The deflection is 9.16 mm. This is less than 13.33 mm, which is the allowable section. The section is safe. Now, the ratios B by TF, D by TW, based on the ratio whatever we have calculated above, it can be classified as plastic. Section classification is immaterial. What is more important is whether web buckling is taking place or not. If web buckling takes place, then ZE should be used. If web buckling is not taking place, then we can use ZP. D by TW ratio is the most important. Section classification is immaterial. It is irrelevant. If for the sake of academic interest, from the values calculated above for B by TF and D by DW, the section classification is plastic. This is only for academic interest. Otherwise, it doesn't have any relevance. Hello friends, please visit my site https://rgnsite.wordpress.com. My website https://rgnsite.wordpress.com. Here about 500 university questions and answers are available on various structural engineering subjects like strength of materials, theory of structures, concrete design, steel design, matrix methods, etc. The download is free. About 500 university questions are available on various structural engineering subjects. The download is free. Please make use of it. Website is rgnsite.wordpress.com. rgnsite.wordpress.com. Thank you.